If we combine the ZZ and gamma gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations.
This can be considered as truly a historic moment that is most certainly one of the most impactful in all of physics. But to understand as to why that is, first we must look much further back in the past. The basic idea was stipulated all the way back in ancient Greece. By splitting something in half enough times, it will eventually lead you to a fundamental, unbreakable unit that everything is built from. Despite the obvious nature of the idea, the first modern version of the atomic theory wasn't proposed until 1803 by John Dalton, and even then it followed quite closely to the already established philosophical idea, with the main addition being the explanation of chemical reactions. This model was first reformed in 1904 by J.J. Thomson as a result of the discovery of the electron in 1897, resulting in the famous plum pudding model, setting negatively charged electrons to be distributed within a larger positively charged mass in order for the whole to remain neutral. This was refined further shortly after by Ernest Rutherford in 1909, as a result of the golden leaf experiment, giving us a familiar-looking model of the atom. The golden leaf experiment revealed many things about the structure of the atom itself, leaving us with a densely compact positively charged nucleus that is surrounded by smaller negatively charged electrons. And now, with the addition of the first direct experimental proofs of the existence of atoms and the newly understood quantum energy levels, it caused two major changes to take place. First, with Bohr's planetary atomic model in 1913, placing electrons at distinct energy levels around the nucleus, and secondly, with Schrödinger's electron cloud model in 1926, giving rise to representing the probabilistic nature of electrons, with this being the model that is still used to this day. But despite learning a lot about the atom's apparent structure, many things remained unknown about their fundamental structure. First of all, the concept that the name atom was built upon, the fact that it is the indivisible smallest unit of matter, had already been disproved by the existence of the electron, and was about to be even further reduced in 1932 with the discovery of the neutron, resulting in having even the tiny dense nucleus be made up of two different subatomic particles. But the division did not end there either. In 1968, partons were discovered thanks to the SLAC accelerator. These were point-like particles that made up the protons and neutrons themselves, making them take the role of the fundamental building blocks. These point-like particles were later confirmed to be the up and down quarks, when further experiments showed the existence of additional flavor of quarks, pushing the confirmation of the 1964 quark model. All of these discoveries end up giving us a standard model for the fundamental particles that make up the universe. Even though these are the current fundamental particles that we know of, it does not mean that they are the last of the subdivisions, and maybe whenever they decide to get off their asses and build that solar system-wide particle accelerator, we'll know if there are more of them. However, the problem that shows itself is that only knowing the particles themselves is only half of the story. What is equally as important is knowing how these particles interact with each other. And this is where force carriers come in. The standard model becomes complete with the integration of the photon for the electromagnetic interactions, the gluon for the strong nuclear force, and the W and Z bosons for the weak nuclear force, with one of the forces being conveniently missing. The theory behind the force carriers is built around symmetry. You obviously want mathematical equations that are invariant and will always work no matter for space or time transformations, giving you consistent predictions. A global symmetry can be easily achieved by simply collectively changing a parameter throughout the whole system, meaning that overall no real change has taken place, just that the values have been uniformly shifted. Local symmetry, however, is far more difficult, since there is a need for constant corrections for the symmetry to be maintained. Think of it like a compass constantly needing to change the direction it is pointing towards as you are turning. Those local corrections are generated through a gauge field. And much like the compass example, perhaps there is a need for a correction in the field, while that correction is an interaction between the particles, which in turn is what we observe as a force being exerted. Different fields represent different forces, and the excitation of those fields are the force-carrying bosons themselves, meaning that a fundamental property of subatomic particles, such as their charge, results from the strength of interaction between that particle and the gauge field itself, and the electromagnetic forces are simply the representation of the corrections between that particle and the electric field, with the adjustments being the reason that local symmetry is maintained. But despite the elegance of the gauge field theory, they are still built upon maths, and more specifically transformations, which are what maintain that symmetry. But the maths itself is quite sensitive, and one of the parameters that the mathematical model is unable to handle is mass. And here is where we have a problem. There are two different roads that we can take, but both are not ideal. Either the gauge symmetries are wrong and need to be broken for mass to have its place, resulting in unpredictability in normalization and losing any predictive power when it comes to looking at higher energies, aka the whole model is wrong and needs to be rewritten. Or the W and Z bosons are massless, just like the photons and gluons, avoiding the problem altogether. However, experiments have shown not only that they do have mass, but they are actually one of the heaviest particles in the entire model, only being outdone by the top quark. And so we need gauge transformations to be maintained for predictability and explanation of the fundamental nature of the fundamental forces, but they are also incompatible with mass being part of the equation, mass which experiments have shown to very much exist and has to be part of the equation. So, was all of that work wasted then? Is the whole thing wrong? Well, a lot of people set out to find out just that. So many in fact that in 1964, several different groups, independently of each other, had come up with very similar solutions. A field for mass. Think of an electrical conductor and insulator. The conductor allows for electrical charge to easily flow through it, whereas the insulator is causing a resistive force, making it more difficult for charge to flow through. Upon a similar idea was a theory of the field of mass built on, now known as the Higgs field. All particles pass through the field. However much they interact with it results in their assigned mass. If they are unaffected, they are massless. However, the stronger they interact, the heavier the particle is, the more resistive force it is experiencing, which translates to its mass. It is like the reverse of the previous example. Instead of changing the medium that the charge is flowing through, now the medium is constant, but different particles react to it differently. This allows for the gauge symmetries to remain valid during transformations, with the interactions of the force carriers still following the same principles. But what the additional Higgs field changes is the underlying structure of the vacuum in which these interactions take place. The Higgs field naturally settles in a state of lowest potential energy, giving the vacuum a non-zero value. This results in it spontaneously breaking the symmetry, with the underlying laws still being symmetrical but now taking place in a non-symmetrical vacuum, giving the particle masses that we observe. But if you remember when I previously mentioned the different gauge fields for the fundamental forces, the excitation of those fields were the resultant force carrier particles. So there must also be a particle for the excitation of the Higgs field, making this the easiest way of testing the theory's validity. Much like most of the subatomic particles, so too the Higgs boson is also very unstable, meaning that it only exists for a very short period of time. But how do we go about creating it in the first place? At the early beginning of particle accelerators in the 1930s, there were quite a few options for different types of accelerators, all with the simple idea of smashing particles to see what they were made of. Originally, this was achieved by accelerating a proton to as high velocity as possible and firing it onto a fixed target. Due to the high energies of the event, subatomic particles would fly all over the place and detectors surrounding the target would make their measurements. The most famous of the designs was the cyclotron, and to understand its unique shape, there is but one simple equation that will explain it. If we have a look at the magnetic force equation, we can see how the force is always applied perpendicular to the velocity, meaning that the force changes the direction of motion in a circular path. Therefore, by taking the equation of circular motion and equating the two of them, we end up with this one equation. This equation simply tells us that with the mass, charge and magnetic field remaining constant, as the velocity increases, via the electric field in this case, the radius of the path will also increase, resulting in an outward spiral. However, this also puts a limit to the distance that the particle can be accelerated for, since at some point the size of the cyclotron would be getting ridiculous. The first major innovation came in the 1950s, with the invention of the synchrotrons, where by managing to increase the magnetic field in sync to the increase in velocity, you're capable of continuing to increase that velocity but maintaining a circular path that doesn't change into a spiral, allowing for much higher velocities and energies to be achieved, notably with the 1954 Bevatron confirming the existence of the antiproton. But all of this was still achieved by using fixed target accelerators, and now it was time to move on towards the much more familiar colliders. These accelerators take two beams and collide them against each other, electron-positron, proton-proton, proton-antiproton, all leading to a number of breakthrough discoveries being made. So what exactly was it that they were looking for? When two protons collide at nearly the speed of light, a sea of particles spread in all directions, with many of those particles only existing for fractions of a second. And the task of identifying all of those particles falls on these detectors. In order to achieve this, they hold different layers, each with their own use case, resulting in a complete image of the collision and its outcome, with exact measurements of the particles that were created, their energies, trajectories, charge, and momentum. Like mentioned before, the Higgs boson is very short-lived, as it quickly decays. In fact, it decays so fast that a direct detection of the Higgs boson itself is not possible, as it is created right in the middle of the collision and the boson will never make it to the detectors. But the remnants of its decay will, and there are three decays that are the most significant that CERN was searching for, with each one of them having a very specific signature. The two-photon decay might seem quite insignificant due to the large number of photons that are produced during a collision, but surprisingly, this is the method that provides us with one of the most famous pieces of data surrounding the Higgs. Photons produce a very clear signature that the high energy resolution detectors can pick up, and from that, use the direction and energy to reconstruct the invariant mass of the process that produced those two photons. Like I mentioned before, there are many processes that generate photons during and after a collision, and so this creates a smooth background of energies, but due to the Higgs having a high mass, it means that there should be an increase in the 125 GeV range, indicating the presence of the Higgs boson that has decayed. This background and bump cannot be built from just a handful of observations. They require enormous amounts of data, both due to the rarity of the decay, but also for the clarity of the data. The second decay is the 2Z boson decay, that are then turned into 4 leptons. 4 lepton events are very rare in nature, and seeing 4 highly energetic leptons that have isolated tracks allows for the precise reconstruction of the initial mass, and therefore another clear increase in energy at the 125 GeV mark. And even though this event is extremely rare, its level of accuracy more than makes up for it, as it is the clearest indication that the Higgs boson was present. The last of the decays is crucial not for its clarity or accuracy, but rather for its confirmation that the Higgs operates as predicted by the theory. By having the Higgs decay into 2 W bosons, it shows that it interacts with a weak nuclear force. The secondary decay generates 2 close-angle leptons, which can confirm this specific chain. But the unfortunate thing is that the rest of the energy is carried out by neutrinos, which escape detection, and therefore no energy bump can be constructed. When all of the data from these observations is combined, it results in a sharp bump in energy. And like mentioned before, this is only achieved after millions of collisions and billions of data points. Just seeing the presence of Higgs boson once or twice is not enough to be seen as a confirmation. There is a need for a level of statistical significance. Sigma is just a quick way of saying standard deviation, which tells us how likely it is for a piece of data to be genuine rather than it being formed by random fluctuations. The greater the standard deviation, the more likely it is that the result is accurate, with the standard for scientific discoveries being 5 sigma, giving it a 1 in 3.5 million chance of it being a random output rather than an actual measurement. And finally, in 2012, that level of 5 standard deviations was reached for the Higgs boson. When you compare the mass of a proton, for example, to the rest mass of the 3 quarks that it is built from, we see that when the masses are added together, they only account for approximately 1% of the total mass. So where is the rest coming from then? E equals mc squared is one of the most famous equations, and it describes a very simple relation between mass and energy. It tells us that a small amount of mass can be translated into a large amount of energy and vice versa, with the most common application of that equation being when talking about bonding energies. This is a bit different than that, but it has the same idea behind it. Quarks contain a very high amount of kinetic and potential energy that arrives from their confined QCD nature. In addition, quarks don't simply exist in triplets, they are linked together by gluons, and they are constantly exchanged between those 3 quarks, keeping them glued together, generating a powerful gluon field. These 2 forms of additional energy make up the missing 99% of the mass of the proton, since mass and energy are interchangeable. Thus, the hollow nature of subatomic particles makes it seem as if all of that trouble had been for nothing, since the Higgs field only really contributes that last 1%. However, there is a reason as to why it was coined as the God particle, because despite what appears as a small contribution towards the total mass, without that last 1%, electrons would not be able to link with protons and neutrons to form atoms. Therefore, the building blocks of our entire universe, and consequently the world itself, would not exist bar the clusters of free subatomic particles.